So in this video, I'm going to explain how to implement binary search tree in C program. So, so this is the program for implementing this binary search tree. So before jumping into this video, these are the some things you should know to understand binary search tree program in C. So first of all, you should know how to implement structure in a C program, then pointers in C, then how to implement recursion. So the main use of recursion is when you want to implement some data structure like a tree or graph or something like that. You should know recursion. If you don't know recursion, then you can implement the same program in other methods using conditional statements and loop statement, but it will take a lot of programming lines. In our program, it's only 53 lines. If you are implementing this without recursion, then it would have taken like a 200 or 300 lines of code. So you should know recursion, and you should have some understanding of the malloc function used for dynamic memory allocation in C. So coming to the program, I will also show this is the tree that we are binary search tree we are going to implement using our program. So when we implement a tree data structure in C program, we don't have any means to print the tree as such. So what we do, or what I do, is print the pre-order, in-order or post-order traversal of the tree. In this case, I am printing the pre-order traversal of the tree to make sure we have the tree right in the memory of our computer. Okay. So don't get confused with the pre-order traversal and this one. This is the order in which we are going to give the input to our program. So I will show the step-by-step procedure of doing this, implementing this program in C. So coming to the program code. So we know these header files of the program. I guess you all know that. Then we need a structure for implementing our tree. This node represents each node of our tree. Then it has a pointer to its left child of the same data type, and it also have a pointer to its right child, and this is the data part. Here we store the data of our node. So this is something like this is how our node will be allocated in the memory. It will have a pointer to its left child, it will have a pointer to its right child. This is where we store our data. Okay, so this part is just easy. You can see we are reading the number of elements. If we have 5 elements, then we will have this loop executing 5 times and reading and inserting 5 elements. So this statement, this is we are actually declaring a structure pointer root, and we are initializing its value as null, initially null. Then we read each element one by one. So we read, okay, in this program our first element that we want to insert is 8. In the first iteration we read the value 8 and store it in the variable num, and we call this insert function with the value of num as 8 and root as null. Initially root is null and our value is 8, and we are going to this insert function. In the insert function we have the data as 8 and this root as null. So here this if statement, we are checking if root is null. Yes, initially the root is null. So what we do here is we dynamically allocate some memory, this using this malloc function. This is the reason why I use this header file stdlib. Stdlib is that header file is required for using this malloc function. So if you don't know the working of malloc function, I really recommend you guys reading this page. It has a very good explanation of the malloc function. So coming back to our program, so the malloc function will allocate some memory which is equal to the size of our structure node, our node structure, and we will have the address of the memory location in the temporary variable temp. Is a pointer. So I assume you know the arrow operator. This is called the arrow operator. It is used in case of structure pointer. Okay, So we have the address of our currently allocated memory in this variable temp, pointer temp, and using this arrow operator we are storing the data. Our data was 8. We are storing the data 8 to that memory location, and initializing, since it doesn't have a left child or right child, we are initializing that position as null. So after executing this statement, our tree will be something like this one. Now memory will have a structure, and its data part is stored as 8, and its left child and right child as null. Okay, I hope it's clear. So in the second iteration, the element we want to insert is 5. So coming to this code, in the second iteration, we read an element 5 and store it in the variable num, and we again call this insert function with 5 and the address of root, address of our root element. This is a pointer which contains the address of our first element or the root element, which is 8. So we reach coming to this insert function. We have the element 5 and the address of the root. We check if it is null. If root is null, no, root is not null. Root is currently pointing to the element 8. So this condition is false. So we coming to the else statement. We are checking if the data is less than the data at the root. So we are checking if 5 is less than 8. Yes, it is true. So this part, this root of data, means we are checking the taking the data stored in this. We are taking the data stored in the root. So 5 is less than 8. So this condition is true. So that means in binary circuitry, if an element is less than one element, then it will definitely go to its left subtree. So we are again recursively calling this insert function with the data 5, and we are passing the address of root of left. Root of left means root is actually 8. Root of left means null. This is point to this location, which is actually null. So in this recursive call, we are again reaching there, this position, and the data is 5, and we have null value here. So we are checking if root is null. Yes, root is null. This null value come from this position. When we call this root of left, it is actually pointing to this part, so it is null. So this condition is true. So we are dynamically allocating a memory location for of the data type node, and we are using the arrow operator to insert the data as 5, and we are making its left child and right child as null values. So we created a memory location and stored data 5 there, and its left child and its right child position as null. 2 pointers. These are 2 pointers. We are making it null. So after that we are returning a temp. What is temp? Temp is a pointer. It point to the memory location where this element, this node is stored. So we are returning its address of this element. So this address, when we after that we return from this recursive call and we move back to our previous position, and it returned the address of 5, address of this element, and we are storing it as root of left. What is this root? Before that recursive call, root was actually 8. So we are storing that address to this position, root of left, in the left as the left child. In the position of the left child, we are storing the address of 5. So after the second iteration, we have something like this. So I hope it is clear. So in the next iteration, the third element we want to insert is 12. So in the third iteration, we are reading the value 12 and storing it in the variable num, and we are calling the insert function. One thing that you should notice, we are not actually changing the value of this variable. It is always the same. Why? Because after each recursive call, when the recursion is over, we are after this if and else statement, we are reaching this statement. It is actually returning the root itself. It is not, the value of root is never altered anywhere in this code. So this function will, after all these recursive call and insertion, will return the initial value of root itself. So this variable is never changing. You should note that. Now don't get confused with that. Okay, in the third iteration we want to insert the element 12, and we are reading it and storing it in the variable num, and we are calling the insert function, and we are reaching here, and we check if root is null. Root is pointing to 8, it is not null. So we are going to this else statement. We are checking if the data is less than 8. No, it is not less than 12, is not less than 8. So it is also false. We are reaching this else statement. So we want to insert. So 12 is greater than 8. So it means 12 should be in the right subtree of 8. So we are calling the recursive. We have a recursive call here. We are calling the insert function with the data as 12 and giving the address of root of right. Root of right means this value. Root of right is actually null. Currently root of right is null. Root is 8 and it doesn't have any right child, so that is null. So in the insert function we have the data as 12 and the root as null. So we check if the root is null. Yes. So what this line actually does is this become null when we reach a leaf node. We can, in a binary search tree, we can only insert elements in the leaf node. So when root is null means there is no element there, and we should create a new element there. That is a leaf node. That is what it is. So we dynamically allocate some memory for storing our structure, for storing our node, and we insert the data. We make its left child and right child as null. Okay, so we create a data, we create a node and insert the data, and its left child and right child as null. We take the values as null. Then we are returning the address of that element, address of that memory location. That means the address of this node. This node that way. So we are returning the address of that memory location. It's a return statement. We are going back to the previous call, and the value returned, that is the address of 12, is storing to root of right. What was root of right? Root of right was actually null. After that call we have the address of 12 here. It's pointing to 12. So after the third iteration, this is what our tree will look like in the memory. So in the next iteration, the element we want to insert is 10. Okay, so we are calling the insert function with the value in num as 10 and the address of root. Root means the address of 8. We again reaching this insert function. We check if root is null. No, root is not null. So that condition is false. When we are reaching this else statement, we are checking if data less than root of data. We are checking if 10 is less than 8. No, that is false. So we reach this else statement. And so since 10 is greater than 8 means we should definitely insert 10 to the right subtree of 8. So we are calling this insert function, passing the data as 10 and the address of root of right. We are actually passing this address, root of right. Root of right means this value. So one thing we should notice in this iteration, root of right is not null, it is actually pointing to 12. So we again call this recursion, we reach there, and this value, the value we pass from this variable root of right is here, and it is pointing to 12 and the data is 10. So we check if root is equal to null. No, it is not null because this position is actually pointing to 12, so it is not null. So we this condition is false. We reach the else statement. We are checking if data is less than root of data. At this point, the root is actually this element. Root means root is pointing to 12. We are checking if 10 is less than 12. Yes, this condition is true. Which means we should insert 10 to the left subtree of 12. So we are again second recursive call. We are again having a recursive call in the with the insert function. We are passing the data which is 10 and root of left. What is root of left? At this point in this call, we are having root as 12 and root of left means this position, this value. Okay, this is the value we are passing as root of left. again reach the recursive call, and we have the data as 10 and root as null because this value was null, and root equal to null. Yes, that condition is true. So we are dynamically allocating a memory location. We are storing the data as 10 and we are making its left child and right child as null and returning the address of that memory location. So we create an element memory location. We store the data as 10 and its left child and right child as null, and we are returning its address, and that returned address is going to be stored as root of left in this recursive call. If you trace this recursive call writing with writing something or drawing it, so it's your own way, you can see that at this point root of left is actually pointing to this position, and we are storing the address of this element to this position. So after inserting the element 10, this is what our tree will look like. So we are inserting the next element, that is 14. I want to insert the element 14, so read the element 14 and store it to the variable num. Then we call the insert function with 14 and the address of root, and he will check if root is null. Root is definitely not null, so this condition is false. Then we go to the else statement and check data is less than root data, which means we're checking if 14 is less than 8. That is false. So we come to this else statement and we again have this recursive call to the insert function, and we pass the data, that is 14, and the address of root of right. What is root of right? This value. So in the next recursive call we are having the data 14 here, and we check if root is null. No, root is not null. Here the root is this value. It is not null, it is pointing 12. So that condition is false. So we come to the else statement and check if data less than root of data. Here root of data means 12, and we are checking if 14 is less than 12. No, it is false. So this condition is also false. Next we come to this else statement. We are again having a recursive call to the insert function, and we pass the data 14, and we are given the address of root of right. Why root of right? Because this 14 is greater than 12, so definitely 14 should go to the right side of 12. So we again having the recursive call to the insert function with the root of right. Root of right means the right position of right pointer of 12, that is null. So when we reach this point, we have the data as 14 and this value is null. The null is coming from this value. Okay, so this condition is true. We are allocating a new memory location and we store the data 14 there, making it left and right child as null, and we make something like this, and after that we are returning the address of 14, address of this element, and that element. So the recursive call is over and coming back. This root of right was actually this position, and we are storing the address of 14 to this position. So after inserting the element 14, our tree will look like this. So after inserting the element 14, our tree will look like this. So we have two more elements. So I think you will understand after all this step how this works. So this is our tree, finished tree. This is how it will look like in the memory. So after all the insert statements are over, now we want to check if our tree was correctly stored. For that, we do a pre-order traversal of our binary search tree. So I have this function preorder. I'm calling it. So and giving the address of our root element, that is 8. Address of, that is a pointer to our root element, to this function, and this function it check if it is null. That means it recursively call the function and it reach a leaf node. That is how it works. So initially it have root pointer pointing to a first element 8. It is just printing root of data, that is printing 8. Then it again has a recursive call. Why is because the pre-order traversal, we first print the root element, then its left element, then its right element. This is how the pre-order traversal goes. So we again having this recursive call with the root of left. We print the first element, then we are having the recursive called root of left, and we reach this point and we print it too. Then again we have a recursive call. After that we again will have this recursive call of root of left, and we reach this element 2. We print that element. Then we again call this root of left and it is null. So we return from that recursive call and we move to its right. So we move from going back to this position and go to root of right. That is, we are moving to this position and we print 6. Then we, after finishing with this element, we go back to this, and we already traversed its left subtree, and we reach this statement and we move to this position, this element, this node. We move to this node and print it. Then we have a recursive call to its left subtree and we print that element. We have again a recursive call to left, but it is null, so return from it. We call it right subtree, no right subtree, it is also null. So we reach this position or this node. Then we again will have this, we already traversed left subtree, then we move to its right subtree and we print that element too. So our pre-order traversal is that is how the pre-order traversal of this tree will look like. So now I will run this program and show the output. I'm compiling it. Now, so in this program we have, in our binary search tree, we have 7 elements. So I'm giving the number of elements as 7 and I'm entering the elements in a binary search tree, that is 8, 2 and 6, and we have the pre-order traversal of our binary search tree, and you can see it is same as what we expected. So our program was correct and our binary search tree is so stored like this in the memory. So we cannot actually print or display the tree as such. So what we normally do is print the traversal of our tree and check if it is correct. So this means our program was actually, this program is there in my website. I posted the link to that program in the description below. If you have any doubts, you can comment it below. I will answer it. And if you like this video, like it, share it, and subscribe to my channel. Thank you for watching. Have a nice day.